Welcome everyone, come back. And today, our first talk is given by the Ved Datar. We are given the talk. The title is the minimal source and singular solution for complex Hessian equations. Please welcome.
Thanks for the introduction, and thanks to the organizers for another opportunity to come back. Over a year back, I had not visited the UK at all, but in the last 1 year, I've visited 3 times now. So, anyway, also, I would like to apologize to some of the members in the audience who were there for my talk in February, because it's going to be, there's going to be a considerable overlap. But there would be two main differences. One, it's a slide talk instead of a board talk. I'm not sure if that's a good thing. But the second difference is that because it's a slide talk, it allows me to maybe spend a little time on deformed Hermitian-Young-Mills equations, which I didn't really talk about in February. So there'll hopefully at least be something new to take away. Okay, so the general theme is going to be the following. So the setup is that let omega be a Kähler metric on X. X is a Kähler manifold. And f is a symmetric function of n real variables with some additional properties, usually some convexity, some monotonicity that guarantees ellipticity of the PD that you're working with, and so on. And then a smooth function h, which is essentially going to be a right-hand side. And then the goal is to usually find a real 1-1 form chi such that the eigenvalues of this omega inverse chi, or the eigenvalues of chi with respect to omega, satisfy this equation. And usually you solve in a particular Kähler class. So with respect to the potential, this actually gives you a second order PDE, right? And then the general sort of fact in this theory is that solvability of these equations usually corresponds to some pointwise condition, which is known as the cone condition. And by integrating the cone condition, one ends up getting some numerical conditions, which in principle are easier to check because they're topological in nature. And it turns out that typically these numerical criteria are actually enough to guarantee solvability. So the main question I would like to address today is, what if the numerical criteria fails, right? So then do you still have a solution, a canonical solution, which of course can no longer be smooth, so a canonical weak singular solution. Right, so here's the outline of my talk. So I'll warm up with this classical theory of the complex Monchampère equation. And then I'll illustrate this theme using two main equations, namely the J equation and the deformed Hermitian-Young-Mills equation. So the first part will be about the J equation, and then, as I said, hopefully I'll have time to also say a few things about the DHYM equations. Okay, so the setting is let Xn omega be an n-dimensional Kähler manifold, and suppose beta is the class of omega. I'll denote the Kähler cone of X by the script K, and suppose alpha is some 1-1 real closed form, not yet positive, but soon I'll restrict to, at least for the J equation, I'll restrict to alpha being a positive class. But right now alpha is just some real 1-1 class. Then of course there's this famous theorem of Yau, namely Yau's resolution of the Calabi conjecture, that the following are equivalent, that there exists a closed positive real 1-1 form in alpha, which just means that alpha is a Kähler class. This is equivalent to actually solving the complex Monchampère equation in the category of positive forms. And in this case, the constant C can be the constant C can be actually calculated by just integrating out both sides, and it turns out to be just the ratio of these top intersection numbers. So this is of course Yau's well-known theorem. But then in the late 90s, Demay and Pon actually proved that this is equivalent to the following numerical condition. The point is that deciding whether a class is scalar or not involves checking some pointwise conditions, and that's usually hard. And so, of course, in classical algebraic geometry, we had, these conditions like the Nakai criteria and then Seshadri's criteria and so on to check positivity or ampleness of line bundles. This was generalized by Demai and Pon in the transcendental setting, and they showed that for all, it's enough to actually check that for all analytic subsets Z in X, these intersection numbers are positive, right? So in general, you cannot actually take P to be equal to M. So this beta is actually required in the general Kähler setting, because otherwise you get counterexamples even for non-projective torus. So it turns out that these three conditions are equivalent. So essentially, solvability of the complex Monge-Ampere is reduced to checking these sorts of intersection theoretic conditions. Okay, so now natural question is, can one solve the complex Monge-Ampere in possibly non-Kähler classes? So it turns out you still do need some sort of positivity, some sort of weak positivity. So we say that alpha is pseudo-effective if there exists a closed positive current in alpha, and we say that if it's big if there exists a strictly positive current, so that's called usually a Kähler current. That just means that T is lower bounded by epsilon times omega for some epsilon positive.
So does that definition make sense if X is not a Kähler manifold? Does it make sense in this condition?
Probably not, but I think for Fujiki class, I think you can still, if it's bimeromorphic to, I guess, right. So the bigness, does make sense for even any compact complex manifold. It's just that you replace omega by some, Hermitian positive form. Yeah, that's fine. But many of these things that I'm going to say also probably make sense for manifolds of Fujiki class, but I'm not sure. Right, but anyway, this definition just requires compact complex. So we denote the set of all big classes by script B, and then B is an open convex cone, and it turns out that the pseudo-effective cone is actually just the closure of the big cone. So this is somehow similar to the situation with the Neff and the ample cones. The Neff cone is the closure of the Kähler cone. So then we saw in the talk of KY that to each big class one can associate a certain number invariant called as the volume. In his lecture, he defined this volume by taking the supremum over the supremum over a set of currents with analytic singularities. I want to actually take the supremum over a slightly larger class of currents, namely all positive currents. But then you have to replace the usual Monge-Ampere operator by this thing called as the non-pluripolar current. It turns out because of Demai's regularization theorem that the definition of volume that KY gave and this definition are the same. But there's a good excuse to sort of introduce the non-pluripolar product. I'm not going to define it because it's a bit technical, but all that we really care about is that it's a way of taking a wedge product of currents that may not have locally bounded potentials. And the point is, if you take this product, then let's say you have P11 currents and you close positive 11 currents, you take the P-fold non-pluripolar product, then it turns out that it gives you a closed positive PP current that does not put mass on pluripolar sets. So it's basically ignores sets which are singular sets of quasi-PSH functions, right? So for instance, if these TIs have what is called as a small unbounded locus, which means that their potentials are actually bounded outside of a pluripolar set. So for instance, an example is that if they have analytic singularities, then this is basically a trivial extension of this usual Monge-Ampere product calculated, or the usual wedge product calculated on the complement of this pluripolar set.
Excuse me, here you are in the non-Kähler setting, right? You are in the non-Kähler setting.
No, I'm in the Kähler setting.
This is the Kähler setting.
Yeah, everything is in the Kähler setting. I guess Rui's question was about the non-Kähler setting, but yeah, everything is in the Kähler setting. Yeah. So So then the optimal existence result is this theorem due to Buxom, Esidiu, Gedge, and Zeriahi, which says that if there's a big class, then in fact you can find a unique current T in alpha so that you can solve this sort of version of the Monge-Ampere equation. So in fact, in their theorem, you can replace omega to the n by any measure that does not charge pluripolar sets, but I've stated it in this form because it goes well with the theme of the talk. And then of course, this constant C is precisely the volume of alpha divided by beta to the n. So it's a ratio of two invariants. Okay, and then a remark is that by the Fujita approximation, or more specifically the transcendental version of Fujita's approximation due to Buxom, one can actually write this C as a supremum of these quotients, where you take the supremum over all possible modifications of x and all possible effective divisors d, so that pi star alpha minus d is nef and big. Okay. So this is sort of the main motivation for us to define an invariant that I'm going to define shortly.
So then this supremum is thing.
It's
If that T solves that equation, then the supremum for the function.
right, but that T may not have analytic singularities. So
Like it's attained when you do the bigger class of currents.
right. So in fact, I mean, the volume actually is attained by these things called as, currents with minimal singularities, right? So, yeah. Right. So with this motivation, let's now move over to the J equation. So the setup now is that again, xn omega is going to be a fixed scalar manifold with beta being the class of omega. And now alpha is going to be another Kähler class. So then in the J equation, we actually solve for a Kähler form chi in alpha so that the trace of omega with respect to chi is mu. Right? Or equivalently, one can write this as an equation for nn forms. And then by integrating, you can check that this constant is actually a ratio of two intersection numbers. Right, and then another nice way of, especially if you're a PD person, a nice way to think about these equations is to look at the eigenvalues. And in terms of the eigenvalues, the equation is that the sum of the reciprocals is a constant. So the origin story, I'm not going to go into that, but I just wanted one line so that it can connect to the theme of this workshop. The origin story is a paper that a survey article that not a survey article but an article that Donaldson wrote on moment maps and diffeomorphisms, and then this was sort of another perspective on this equation was brought in by Chen and possibly also Chen Tian when one writes the formula for the Mabuchi energy, the decomposition formula. I think Hattori mentioned that yesterday. There's the entropy part, and then there's an additional part. The additional part is a functional called as the J functional, and if you sort of generalize that J functional, the Euler-Lagrange equations of that are precisely the it's precisely the J equation, right? And so particularly when C1 is negative, solvability of the J equation actually tells you a little bit about whether you have CSCK metrics in line bundles in a certain range, right? Okay, so anyway, but for us, all that is not going to be important. This is, we are just going to talk about this for its own intrinsic interest because in PDEs, these sort of sigma k problems have been studied for a long time, and they're sort of interesting for their own intrinsic reason. Okay, so let's take the simplest sort of case, namely that of surfaces. So n is equal to 2, then one can do what every high school kid learns how to do, is to complete squares, and by completing squares, one can reduce the J equation to a complex Monge-Ampere, and then of course Yau and Dimai and Pons Nakai criteria tells you exactly when you have a solution, right? So you have a solution if and only if alpha minus 1 by mu beta is scalar, and if and only if these intersection numbers, this inequality for the intersection numbers is satisfied. Okay, so the surface case is easy. In general, what should be the sort of necessary and sufficient condition for solvability? So Donaldson in his survey article had some condition on the Kählerness of a certain class. It turns out that that's actually not correct. There are counterexamples, so one needs a slightly more refined necessary and sufficient condition. So one can start off by doing something silly. You have, the equation is that the summation of the reciprocals is equal to mu. Each of these eigenvalues is positive, so let's just throw away one of the eigenvalues, and then you end up with this inequality, right? So this might seem like something silly, a silly thing to do, but it turns out that you can actually write down this condition in a global invariant form as an inequality, as a positivity condition for n-1, n-1 forms. And it turns out that this, this silly thing actually turns out to be a necessary and sufficient condition. So we call this the cone condition. And in fact, you can, why stop at just dropping one of the eigenvalues? You can drop as many eigenvalues as you want, let's say n minus m of them, and then you end up with these slightly weaker conditions, right? So you have this family of finite family of sort of pointwise conditions, and then like in Demey and Pon, one would ideally like to obtain a numerical condition out of this. So the easiest thing is to try to integrate this on m-dimensional subvarieties, right? Okay, so that turns out to be a necessary and sufficient condition. So the optimal existence theorem for the J equation is the following. So it turns out that the following conditions are equivalent, that there exists a metric chi in alpha which satisfies this weird cone condition. Secondly, there exists a metric chi in alpha which actually solves the J equation. And hence, in particular, this particular solution will also satisfy the cone condition. And the third criteria is that for every analytic subvariety Z, we have this inequality of intersection numbers. Okay, so I should remark on, maybe I should give some credit where it's due. So 1 being equivalent to 2, or 1 implies 2, is actually due to Song and Weinkow. And in fact, I believe they were the first ones to realize that this weird sort of cone condition actually plays an important role in solving the PDE. Then 2 to 3 is of course trivial, as I explained, just by integrating. The crucial part is 3 implies 1, and this was a conjecture due to Lejmi and Zeklihiri, which was finally solved by Gauchen. Although Gauchen didn't quite solve their conjecture, but he obtained a sort of uniform version of their conjecture, which just means that you replace this mu by some mu minus epsilon, right? So you assume something slightly stronger, and then you prove existence. But of course, the sort of key role in this development is played by his paper. And then in collaboration with my colleague Vamsi Pingali, we were able to sort of prove the original Lejmi-Zeklihiri conjecture in the projective case, and then Jian proved this in general. Okay, so now I want to reformulate this slightly in terms of something that looks like, this usual stability implies existence kind of a criteria. So for any analytic subvariety, I want to define this slope mu z, which is simply the dimension times this quotient, right? So in particular, if you take z to be x, then you get back your dimension, your original constant mu. And then we say that that this triple is slope stable. So actually for the J equation, there are various notions of stability, and they're not always necessarily equivalent. But in my case, stability will basically mean the slope stability, which just means that for any analytic subvariety Z, the slope of Z has to be smaller than the global slope. And of course, we say that it's semi-stable if you allow equality, and then unstable if it's not semi-stable. So then the theorem can be reinterpreted as saying that the J equation is a solution if and only if this triple is stable, right? Okay, so now the question is what happens in the unstable case, or even the semi-stable case, but the unstable case is more dramatic. So let me talk about sort of motivating example, and this is in fact the example which made us sort of think about trying to find weak solutions. So there was this old paper of, old as in 10 years back, a paper of Fang and Lai, where they study the convergence of the J-flow on blow-ups of projective manifolds. And the simplest example is, of course, you just take the blow-up of P2. Then it turns out that you can calculate various things very explicitly. So I'm going to assume that by rescaling, my classes are such that the intersection with the exceptional divisor is just 1. So alpha is going to be AH minus E, beta is going to be BH minus E. And for them to be scalar, A and B have to be bigger than 1. Then it turns out that mu is given precisely by this quotient AB minus 1 by A squared minus 1. And then stability is precisely when mu is bigger than 1. In fact, for this particular example, to check stability, you just need to integrate on the exceptional divisor. So that's the -1 curve that destabilizes. So if you integrate on that, you will basically get this, this condition that mu has to be bigger than 1. So then the idea is to try to use Calabi-Ansatz to reduce the PDE to an ODE, and it turns out that it's a very simple linear ODE. So this is not the usual kind of ODE that we solve using Calabi-Ansatz. So the point is that you can write omega as dd bar of u of rho, where rho is this. You think of the blow up as this sort of projective bundle, and then rho is basically just the logarithm of the radial coordinate, essentially. Right, and similarly, you put chi is something like this, and then the Calabi-Ansatz will tell you that u prime and v prime actually map R to 1 comma b and 1 comma a. So then instead of writing the equation in terms of this v, what you do is you write the equation in terms of this map between these moment intervals. Right, and in terms of this psi, which goes from 1 comma a to 1 comma b, it turns out that you get, this J equation is just a simple linear ODE that of course can always be solved. But if you want to solve the J equation, you actually want a solution that's strictly increasing. That's because u and v are both convex functions, so psi has to be a strictly increasing function. So if you look at the general solution, the general solution will be strictly increasing if and only if mu is bigger than 1. Okay? So now what do you do in the unstable case? So it turns out that in the unstable case, if you look at the J flow, so there is a corresponding parabolic flow that I'll come to in a moment. It turns out that if you write it in terms of this psi, you always get a certain limit. So our first job was to understand what that limit is, right? And try to reinterpret it slightly more geometrically. So it turns out that instead of, in the unstable case, instead of sort of looking at the whole interval, I wrote on the wrong board. Anyway, that's fine. So instead of looking on the whole interval, you have to look at the interval, slightly smaller interval, and look for strictly increasing functions from a slightly smaller interval into 1b, solving the same equation, except now, of course, when you integrate both sides, the constant will now change because the boundary conditions have changed. So the constant will depend on S, and you're again looking for increasing solutions, and it turns out that this limiting solution that Fang and Lai found that depended on this parameter lambda, and this lambda is precisely the sort of minimal S for which you have an increasing solution. to those equations. So then it's not very difficult to reinterpret this in the following way, that lambda is actually the minimal S for which this triple, so you start with x alpha beta, which you know is unstable. Then what you do is you just subtract off a little bit of the divisor that is destabilizing, and it turns out that if you subtract enough of it, you will again get into the stable category. So then you take the minimal S for which this triple is stable, and lambda turns out to be precisely that. Right, so this acted as one of the main motivating examples for us. So inspired by this, I'm going to now define what we call the minimal slope. So I call it the global slope here, but I should say the minimal slope. And you can see that the definition is very much inspired by what happens with the volume and Fujita approximation, right? So you take the infimum of these ratios over all divisors D on all modifications such that pi star alpha minus D is big in F, so that the denominator is positive and this triple is semi-stable. So you take the infimum over all such divisors and all such modifications. And then we have the following conjectures that firstly, we conjecture that there exists a unique Kähler current T in alpha which solves this the J equation, but now the wedge product is replaced by this non-pluripolar product, and the main thing is that the slope is now modified. So you no longer solve it with the original slope but with a modified slope. And moreover, we also claim that the zeta is always going to be smaller than the original topological slope whenever this triple is unstable. So whenever this triple is unstable, your J equation is going to be solvable with a slope that's strictly smaller. And we also conjecture that these solutions are actually canonical in the sense that if you look at the J flow, which is given by this equation, it has been known for a long time. In fact, this was proved by Chen that the J flow exists for all time. Okay, so then a natural question is, I mean, by normalizing the potentials, one can always extract an abstract sort of weak L1 limit. So then a natural question is, does that L1 limit actually satisfy, or does that limiting current actually satisfy an equation? And we conjecture that it should satisfy this equation. Okay. So in that sense, solutions to these equations should be in some sense canonical. Okay, so the first theorem, this is joint work with my student Ramesh Mete and Jian Song. Our first theorem is that, in fact, our conjecture holds in the surface case. And in the surface case, you actually do not need to take any modification. So you can actually compute this minimal slope by just taking divisors on your Kähler surface. And so the proof is actually very elementary. The key observation is that for the surface case, if you look at alpha minus mu inverse beta, then this always turns out to be big. So, I mean, this seems a little bit magical at first, but it just follows from a lemma due to Lamari. And it's not quite complicated. I mean, it's quite simple actually. But then once you know that this is big, then one can actually use Zariski decomposition to show that the zeta is actually the unique solution to this volume equation. Once you have equality of these volumes, one can try to solve a complex Monge-Ampere equation, because remember in the surface case, the J equation, you can complete squares to reduce it to a complex Monge-Ampere, and then we can just use BGZ, right? So the proof is not very, I mean, it's actually quite easy. It just relies on this main observation that this class is always big. And I should mention that there's also some related work due to Khalid and Dirichlet on the set of destabilizing curves for the J equation. So it turns out that they also, I mean, the point of their paper is to understand whether there are only to check whether something is unstable or not, you only need to check a finite number of conditions. And it turns out that what they do is that they use this class, take the Zariski decomposition for this, and look at the negative part of the Zariski decomposition. That will be a divisor consisting of finitely many curves. And these are precisely the curves on which can destabilize your triple. Okay, so this is, our work is very closely related to this work of Khalid and Dirichlet. Okay, so another theorem that we prove is we also prove the convergence of the J-flow on some projective bundles. So in these projective bundles, it turns out that conjecture 1 and 2 hold with for metrics with Calabi-Ansatz. But then instead of the zeta that I defined, you actually have to use this slightly different slope, which I call zeta invariant, where you don't have to check all modifications, you only have to take modifications which are blow-ups along the zero section, right? So so it's enough, in the case of these examples with Calabi symmetry, it's actually enough to check, to compute the slope for these restricted class of modifications. So of course, in general, zeta invariant is obviously bigger than zeta, because for zeta you take infimum over all possible modifications, but we actually expect them to be the same. I don't know what the proof is, but this seems like almost an algebraic fact, and we expect them to be the same, but yeah, I don't know how to prove this. Another remark is that the same sort of convergence result was obtained when M is Pn and these line bundles are O of -1 by Fang and Lai. Although, yeah, I should say that their proof seems a bit incomplete. At least we are not able to understand the proof, and so in order to convince ourselves, we had to sort of give an alternate proof of their theorem, and that involves, it still follows by and large the template that they follow, but it requires some new estimates to complete the proof. Right, so maybe I should also end with a few additional, end this section with a few additional remarks that recently Murakami has actually verified this conjecture on the convergence of the J-flow on surfaces in the semi-stable case, and his proof is actually very beautiful. It uses viscosity subsolutions, but it still seems like the general unstable case is still open even on surfaces, because he crucially uses the J functional in his proof, and in the unstable case the J functional is not that useful because it sort of blows up, it goes to -infinity, so it's not as useful. So there's another joint work with my student Shivram and Jian Song, in which we look at the toric case, and I think the toric case is particularly interesting because it turns out, again, like for Calabi-Ansatz, in the toric case you can set this problem up as an equation satisfied by a map between moment polytopes. And it actually turns out this psi actually satisfies a linear first order PDE. But then the point is that you may not always have a solution. In order to have a solution, you might actually have to shrink your polytope. So the polytope itself is also part of the unknown, part of the problem. And this sort of gels in well with our conjectures, because essentially, if you take toric modifications, then or if you take toric blow-ups, that would basically imply that you chop off some face or some edge of the polytope, so that instead of solving the problem on the original polytope, you're now solving the problem on a slightly smaller sub-polytope, right? And so this, I think, just as a purely real PD problem, I think it's interesting. It's just a linear real PD, but the domain is basically part of the problem. It's an unknown. So this is sort of some joint work with Shivram and Jian. Okay, so that completes my completes this discussion about the J equation. Any questions or comments?
Well, in that Calabi answered construction,
Right.
you take n plus 1 sums of the same line bundle.
Right.
And so have you tried seeing what happens if you?
Yeah, so I don't know. I think it should be similar. I don't think there is. Right. So the reason we do this is because in the original Fungenlai thing, they basically had tensor products or direct sums of O minus ones, and so I don't think there'll be any substantial sort of technical issues.
In the toric case,
Right.
I guess one dimension, like in general, you could chop off things so that the fan changes.
Right.
But maybe in the surface case then, since you said you could.
Right, so in the surface case, maybe you don't have to. Right, so you just have to move some of the edges in.
Yeah.
Right. And in fact, you can just play around this little bit, and you can see that if you sort of move things a lot, then the triples become stable. So as long as I think this class alpha is somehow small, these triples will always be stable. So then the point is to find sort of this optimal thing where you have a solution. Right. So maybe I'll now move on to the deformed Hermitian-Young-Mills equations. So in this case now, alpha is allowed to be any real class, not necessarily Kähler, and chi is a smooth background 1-1 form. Then the deformed Hermitian-Young-Mills equation is to find a chi phi which satisfies this horrible looking equation. But this somehow, I think the main motivation was that this is somehow supposed to be the mirror to the special Lagrangian equation, or at least a special case of that. In general, you have to also look at sort of vector bundle versions of. So in some sense, the equation that I'm writing down is sort of the line bundle version of the deformed Hermitian-Young-Mills. But in general, you have to also look at vector bundle versions, which are much more complicated because this is a scalar equation. The vector bundle versions will be sort of PD for systems. So I'm going to always assume that my theta hat is normalized so that it's in this range 0 to pi. So this is called the supercritical range. So for a general form, we define this Lagrangian phase operator as this. And it turns out from a purely PD perspective, this equation is slightly better than this equation. But on the other hand, here it's actually important what choice of normalization you make for theta hat. So my theta hat is always going to be between 0 and pi. And the reason is that in 0 and pi, cotangent is monotonic. So one can now drop one of these arc cotangents and again get something analogous to a cone condition. Right? So this is why this supercritical regime, namely where theta hat is between 0 and pi, plays an important role in this theory. Anyway, so one gets a similar necessary cone condition. And again, in the surface case, one can again just complete squares, and with applying Yau and Dimai and Pon, one gets an optimal existence result. So then, of course, the natural question is, what should be the case for higher dimensions? And then there's this, based on the Legendre-Zeklidy conjecture, Jacob and Yau and maybe Collins put forward a conjecture for the deformed Hermitian-Young-Mills. So it turns out that their original conjecture is not quite correct, but a slight modification of their conjecture actually holds. And so the optimal existence result was once again in the uniform case was obtained by Gauchen, and then in the non-uniform case by Chuli and Takahashi. And so it turns out that you have a solution if and only for every analytic subvariety, if you compute these intersection numbers, they have to be positive. Now there's one important difference with the Nakai criteria for the J equation, namely there is this additional gamma that shows up. And it turns out that this gamma is actually required. Without this gamma, you would actually have counterexamples again on some toruses, some non-projective toruses. So, so that's the main difference with the J equation. On the other hand, for the J equation, the J equation is always solvable on a torus. So,
but the gamma doesn't come in projective.
Right. So gamma doesn't come in the projective case because you can just take gamma to be the hyperplane class, right? So yeah, so the gamma, you can get rid of it in the projective case. This is actually similar to what happens even in Demai and Pons Nakai criteria, where you had this alpha raised to something, wedge beta raised to something. You can actually get rid of that beta in the projective case and get back to the sort of classical Nakai criteria.
You need to assume X.
Pardon?
X is projective.
No, here X doesn't have to be projective. No. So that's what, as Lars was pointing out, if you assume X is projective, you can actually drop this gamma. Right? Okay, so I should also mention that this theorem was proved for projective threefolds using the method in the paper with Vamsi by Vamsi's student Ashirvad. And it was unfortunately, I think he was, as he was preparing his preprint, the Chuli Takahashi paper appeared, and this is one of these things where, I guess as a student, it's particularly unlucky if this happens to you, but anyway, it's now still published, but yeah, I guess it would have gotten more traction if it would have appeared before Chuli Takahashi. Anyway, so then, for the deformed Hermitian Young-Mills, our main theorem is the following. Again, in the surface case, we now assume that alpha dot beta is positive. The reason is that if you look at this constant C naught, that has alpha dot beta in the denominator, so you don't want that to be 0. So then there are two cases, either alpha dot beta is positive or it's negative, and by just replacing alpha by minus alpha, you can assume that alpha dot beta is positive. Okay, so then in that case, our main theorem is exactly analogous to what we had in the case of the J equation, that you always have a singular solution even in the unstable case, where this slope, the cotangent is now replaced by this psi, and this psi has another similar characterization in terms of quotients of intersection numbers. And again, the key point is to actually show that alpha minus C naught beta is always big, under the assumption alpha dot beta is positive. Okay, so this is our main result in the surface case for deformed Hermitian Young-Mills. So maybe let me end by maybe talking a little bit about convergence of one of the flows to this limiting solution. So before that, let me just again talk about this very simple example of blow up of P2. So here again, everything is very explicit. You assume that your class alpha is given by P times H minus Q times E. It need not be Kähler, and beta is given by that, where B is bigger than 1. Then you can actually explicitly compute all these sort of numbers. And in this case, you can actually explicitly check that alpha minus C naught beta is actually big by just doing this calculation explicitly. And that actually results in two inequalities, namely this inequality and then P bigger than C naught times B. So then there's this result of Jacob and Shu, which where they studied the deformed Hermitian Young-Mills equation on blow up of Pn. So this was before Gauchen's paper appeared, or maybe just afterwards, but they essentially classified all the solutions on blow-ups of Pn. And in this particular example of blow-up of P2, they showed that there's a smooth solution if and only if Q is bigger than C naught and P is bigger than C naught B. But as I observed here, just by the fact that alpha minus C naught beta is big, you actually get this condition for free. So in fact, they're assuming alpha dot beta is positive, their theorem is that you have a solution if and only if Q is bigger than C naught. Okay, and the proof is actually simple. Again, you do something similar to what I did there, except now instead of instead of a map from this interval to this interval, you go in the other direction because the interval for V prime, I mean, you don't know what that interval is because the class is not Kähler, right? So you write it in terms of a map going from 1 to B in the other direction. And it turns out that that the deformed Hermitian Young-Mills is actually equivalent to psi lying on this level curve with certain boundary conditions. And then, of course, this is a quadratic equation, so one can just explicitly solve it, and it will have two branches, and essentially you want to decide when it's a single valued function, right? Then you have a smooth solution to the deformed Hermitian Young-Mills, and one can show easily that you have a single valued solution if and only if Q is bigger than C naught. Okay? So anyway, so in this case, one can again ask what happens in the unstable case. As I explained, the unstable case is precisely when Q is smaller than C naught. So in that case, one can explicitly calculate our invariant xi in terms of these numbers B, P, and 1. And one can also explicitly write down what this current is. Okay? So again, natural question is, how canonical are these solutions? So unlike in the case of the J equation in the theory of the deformed Hermitian Young-Mills, there's no unique flow. There are actually multiple flows that people have studied. And to my knowledge, there are three main flows that people like. One was in the original paper by Jacob and Yao. This is called line bundle mean curvature flow. Then there's another flow. So in some sense, I think that's the most natural flow that one can come up with. But from the PD point of view, that uses this Lagrangian phase operator theta. And so from a PD point of view, that's probably the hardest flow to study. So then Takahashi came up with what is called as the tangent flow. And then following Gauchen's paper, it became clear that cotangent is probably a slightly better thing to use. And so around the same time, Fu, Yao, and Zhang came up with what is called the cotangent flow. So that looks like this. So then, of course, one can also study this flow with Calabi symmetry. And so our final theorem is this convergence result for the flow, for the cotangent flow on the blow-up of P2. And we actually show that our flow does converge. If you start with a suitable initial condition, the flow does converge to the limiting current that we, the singular solution that we construct. So unfortunately, this we don't yet have uniqueness, but that's, I think, more to do with laziness and fatigue, I think, rather than sort of technical reasons, because the idea is that our modification of the Fangli proof, part of the problem with the Fangli proof was that, schematically their proof basically first proves convergence for a particular initial data, and then you have to prove some sort of a uniqueness result. That doesn't matter which initial data you begin with, you always have the same limit. And that part of the proof seems to be, or at least we don't understand the proof. So that required a little bit of modification. And I think the same modifications should also work for this, but by that time already the work had sort of taken 2 years and we were, I think, just fatigued. So my student Ramesh, I think these are good things to hand out to your students. So he'll try to work this out and prove this uniqueness result. But more importantly, he's also working out a convergence result in the dimension 3 case, which so convergence result in the unstable case in dimension 3, which I think would be a new result. I don't think anyone has. Adam with one of his Adam Jacob with one of his collaborators posted convergence result for the line bundle mean curvature flow in the semi-stable case, but in the unstable case, as far as I know, in higher dimensions, this would be the first result. So he still has a couple of technicalities to work out, but hopefully he'll publish something by the end of this, post something on arXiv by the end of this this summer. And then I should maybe end with saying that we also have conjectures for the deformed Hermitian-Young-Mills equations, but they're a bit more technical, owing to the fact that alpha a priori has no positivity of any sort, right? So it's not. So yeah, I mean, we do have some conjectures, but we don't have any idea of how optimal they are. And because of that, these examples actually matter, because the more examples we have, the more sort of refined we can make our conjectures in the deformed Hermitian-Young-Mills case. All right, so these are some of the references in case you're interested in this. And yeah, thank you for your attention.
Thank you for the talk. Any other questions or remarks?
In your second part of the Young-Mills equation, is there also a stability interpretation of it, like there is for the J equation?
Right, so you could just define the stability to be whenever those that positivity condition holds. So there is a much more sophisticated notion of stability, which I guess people like Rui, etc., work on, which is Bridgeland stability. But I have no idea how. I mean, they're not obviously connected, because there are some counterexamples. It's not equivalent to this stability, but right. So there are various notions of stability. The simplest one is basically what. I mean, these positivity conditions that I wrote, you can just say that your triple is stable if those positivity conditions are satisfied. Right? But yeah, from maybe a mirror symmetry point of view, I don't know if those are the kind of stability conditions that you want, or you want some Bridgeland type stability conditions.
No. So, as again,